Okay, great. Welcome. Thanks for coming in the last session of the day in a room far, far away from the center of the conference. Today we're going to discuss a proposal for HDFS tiered storage to implement tiering in HDFS, and it's built on top of heterogeneous storage types and policies. So I'm Thomas De Moor, product owner architect at Western Digital. Our division makes an S3 compatible object storage system. And I've been working in Hadoop for a couple of years, mainly around S3A optimizations, the streaming uploaders, yarn support, and actually coming up, if you saw Sanjay Raja's talk yesterday, the rename free committer problem. I think we're very close to cracking it. Steve Loughran, Ryan Blue, doing loads of work there to actually finally finalize that. But for like the last year or so, we've been focusing lots of our efforts on HDFS tiered storage, and together with my coworker, Ewan Higgs.
Hi, I'm Virajat, and I'm a scientist at the Microsoft Cloud and Information Services Lab. Along with Chris, Douglas, in our group, we have been working on this project. So we're going to talk about it in more detail today for about a year now.
So HDFS tiered storage, the idea is to mount and manage remote stores through HDFS. So you see in the top your Hadoop cluster, you have your application there, you have your HDFS in the Hadoop cluster, and then there's the remote store. And so the goal is now to actually marry both worlds. As Virajat said, about a year ago, Chris and Virajat posted a design doc. They presented last year, and it was exactly what they proposed was actually a solution to the problem we were also trying to tackle. So we hopped on the bandwagon, and it's 1 year later now, and we want to give you a status update. So we also presented in Munich. So they presented last year, we presented in Munich. There we really discussed the architecture, the design. Of course, we're going to reiterate that, so you can follow. But we definitely also want to give a progress update, so talking about mounting and about the right path. And there's actually a live demo, so no tricks. Virajat's going to do magic. So why do we want this functionality? What can you achieve with it? So first use case, ephemeral Hadoop clusters. So short-living Hadoop clusters, temporary Hadoop clusters, like Elastic MapReduce on S3 or HD Insight over Azure. So you have persistent data which lives in the cloud store, and then you spin up these Hadoop clusters, which you spin them up, there's nothing there, so you need to actually get your data in. And when you're finished, when your job or pipeline is finished, you want to get your data back out. So there's no like integrated way to do this. And so what people typically do is what I would call workarounds. So you dist-cp copy stuff around, or you say like, I'll only use the remote store. I'll actually don't use the HDFS inside the cluster. So I'll take the performance hit by doing all my I/O to the remote store. Or I'll explicitly, in my application, manage both the local and the remote storage, and yeah, shift everything there, manage it in the application. And that becomes quite tedious, and it's very error-prone. So the goal for this use case is to really, in a transparently abstract away the fact that there are multiple clusters. So really have one HDFS, one instance of HDFS that abstracts away the underlying topology of the clusters. You can retrieve data from the remote cluster to the local cluster, write it back out. And the fact that there's local storage also introduces interesting caching opportunities. So the second use case, every year at Hadoop Summit, you have more and more talks on cloud. Azure, S3, it's like a deployment model which is gaining popularity because it offers efficient storage at an interesting price point, and it also allows for a lot of data flow where the object store can be used for backup, migration, other non-Hadoop parts of your infrastructure can play along with it. So for business planning, it's also quite useful. So this model has been seeing more and more uptake. Of course, you can also replicate it in the private cloud, and that's where we come in, Western Digital. We have an object storage system, ActiveScale, which is S3 compatible. It goes from like a couple of 100 terabytes to 5 petabyte a rack, and then it scales out linearly with racks and objects and throughput. So that's why our interest in S3A and now in this project is big in the Hadoop world. So today, what would you do when you have like an object store? How would you communicate it through the Hadoop compatible file systems? So you can see you have your Hadoop cluster, and it only has the application. So it only has the compute part. There's no HDFS. And you do direct I/O between your application and the remote store using S3A or WASB, or there are a lot of connectors. So this has advantages. It's like it's scalable, it's resilient, because actually the name node function is outsourced to the remote store. So the object store handles the namespace scaling. Of course, and I think also in Sanjay Raja's talk yesterday, it was very apparent that compatible does not mean identical. So this is a use case that can really work for you, but there are also quite some workflows where, yeah, this is far from ideal. So most of these object stores, they're not file systems, so they don't have directories, they don't have appends. There are multiple other inconsistencies, and sometimes these leak abstractions, yeah, they leak through. There's also no data locality, so for really high-performant workloads, yeah, the performance hit is a bit painful. And then the main one, yeah, actually Hadoop admin tools, they're actually HDFS admin tools. So permissions, quota, security, all of these stores, they typically don't integrate with that. You can partly work around this by, again, managing both local and remote, have a local HDFS storage, have the remote store, and managing both in your applications. Again, tedious, error-prone, and you actually don't solve the problem. So for this use case, the goal is really to integrate with HDFS, have data locality for hot data, and remote object storage for cold data, and offer the familiar HDFS abstractions and make the admins happy so their tools work. So the proposed solution, you see our Hadoop cluster with the and we re-add the HDFS layer. So we mount the remote store inside HDFS. The application reads and writes to HDFS, and HDFS will manage and coordinate with the remote storage. So it will write through, or write delayed maybe even later, and then load on demand the data into HDFS. So this is achieved by adding a new storage type provided to the heterogeneous storage types in HDFS. Virajit will give you loads of details on this, so hold on for a while. After the demo, he'll fill you in. So what actually happens, you have the remote namespace in the store. And actually, the remote store can also be HDFS again, so you can mount HDFS and HDFS. It can also be an object store, it can also be whatever you want. So we will mount the remote namespace, and in the HDFS namespace tree, you can now see that there's the subtree with on inode C, which is actually a mount point. You can achieve this by setting a storage policy to actually move data between the tiers. So if you set the storage policy on C, and you say, I want this to be provided, then your data will start moving to the provided store. You can say, I want this to be SSD and provided, then you have on SSD one hot copy inside your cluster, and there will be a replica in the provided store for durability backup. So main benefits is that the user or the application does not know and does not need to know if the data is local or remote. HDFS handles this completely. They abstract away the underlying storages, and they really offer a unified namespace. All the Hadoop admin tools, they just work. So HDFS, the application will not use the remote store credentials. It's HDFS who also manages these credentials. So as far as the application is concerned, they're talking to HDFS. So quota, security, what you have can all be managed like for a legacy cluster. And then there are, yeah, I said it before, caching, prefetching. We really think there are interesting opportunities there. So why is this not trivial? So we want to synchronize the metadata without actually moving the data if it's not necessary. You don't want to mount a bucket in a blob store which has 100,000 files and start copying in all the data. No, you want to actually dynamically page in the blocks on demand you need. caching. So when you page in blocks, you can, in the Hadoop cluster, then cache certain blocks you think were hot, you need multiple times. So caching eviction is then a very interesting challenge there. The remote namespace is, of course, completely separate from your Hadoop cluster, and you also typically don't have control on it. So there can be churn in the remote namespace. People can, behind your back, add data, delete data. So our solution needs to be able to handle that in a more or less sane way. I mean, it's a hard problem. You have to have a sane way of dealing with it. And then handle writes consistency. This is a very important one. The very naive solution would be to say, like, hey, this is a new storage type. We'll just write blocks onto this remote store and we're done. No, you don't want to see blocks on the remote store. You want to maintain the file-to-object mapping. So you want to have writes to make sense. If you take a blob store client and after moving the data to the remote store, the blob store client, like an S3 Boto or a S3 CMD or for Azure, an Azure client, they need to be able to read that data. So you need to map the blocks onto the object on the other side. And then finally, mounting. Mounting is a well-known concept. Storage admins understand it, so let's please try to stay as close as possible to what is like the common accepted way of doing mounts. I promised a demo, so it's a live demo. Let's hope the Wi-Fi is nice. Rajat, go ahead.
Okay, so in this demo, we are going to basically see how we can back up data in an on-prem HDFS cluster to the Azure Blob Storage, and then in Azure, we spin up like a temporary HDFS cluster and be able to access the data through that. Okay, let's see if this works. Oops. That's remote.
I actually saw it the first time last week, so it's hot off the needle. Is the Wi-Fi down?
I think that's the remote desktop. That's.
So if the Wi-Fi is down, we have a backup. It's called LTE.
Okay, just a moment.
Microsoft appears to be down, so maybe Chris can. Any questions on the first part? Maybe to ease it up. Any questions for the part I presented? Go ahead.
It seems that the work is really close to what Alluxio is doing. So can you comment on that? And why would I choose this feature instead of Alluxio?
So Alluxio, they actually put an in-memory file system in between.
Right. So they do caching too, right? Like you guys.
Yeah, but you don't have to do caching here. So you can simply, if you only need it once, you read it once and you're done. You don't have to do caching. So caching, they started off with really doing caching for Spark to like reuse data in multiple containers, in multiple jobs, and to survive crashes on Spark, have your data survive the crashes there. And then they also moved into integrating with, then they moved to also integrating with other storages. Here we're actually doing it the other way around, and we're building it natively into HDFS. So Alluxio, their play is like, we become the center of your data in your entire company. So that's a very bold thing to do. I think HDFS and object stores are further down that path. I'm not saying that they won't get there, but.
So when you store data in an S3 bucket, do you actually store the blocks only? And if you only store the blocks, how do you know if they are lost? Like, in HDFS, there is a heartbeat and a block report and all that. But some of these remote things, like even if it's a remote HDFS cluster, how do you know if the data is there or who takes care of that? Completely of the data, which HDFS generally does. So if I think that this is HDFS and start using it, how do I know?
So definitely with blob stores, typically they're highly available and they're very durable. So the assumption is that the data will be there. And if it's not there, you'll see an error, which is probably, if your data is lost on HDFS, there's no magical way to get it back, of course. Does that answer the question? Or?
Partially, but you also said you can mount a remote HDFS.
Mm-hmm.
So if you mount a remote HDFS because you put the files there, does that HDFS know about this, or does that HDFS see it as a block?
No.
How does that work? So, but, no. In the case of HDFS,
So you would like communicate the block reports of one cluster to the other cluster, or?
that's what I'm asking. How do you only put a block? How does it?
No, it doesn't do per block. Eh? So a file in HDFS becomes a file in the other HDFS. And so we really want to keep that semantic, because otherwise, what's the second HDFS cluster? You see like 7 million dot block, 7 million and 1 dot block, 7 million and 2 dot block. That's not a storage system. It's a block layer. So we don't want that. We really stayed away from the block layer. We want really the file to file or file to object mapping to be there.
Okay, so I think we got remote desktop working, and Murphy's law always wins. So this is an on-prem cluster that we have set up, and oops, okay, and I have a couple of directories here. So let's look at the YCSB directory. So this has a few folders, and particularly suppose I wanted to download or back up the YCSB bin directory. Okay, I think it's a Wi-Fi acting up. Okay, let's try to do it in the end then. So at a high level, how it was supposed to work was, so you have this on-prem HDFS cluster, and by simply setting the storage policy of any directory that you want to back up to Azure, you should be able to back up the data. And then we kind of scan over the data in Azure and get this metadata information from that. And the metadata information is used to start up your Hadoop clusters on Azure. So any directory on your on-prem cluster would have been backed up to a corresponding blob on Azure, and then this could be read through your HDFS cluster on Azure. So any of your analytics jobs on the cloud should be able to read the data that was originally on-prem. So in this work, we actually use two kinds of mounts. So kind of matching the use cases that Thomas talked about before. So the first kind of mounts are ephemeral mounts. So these mounts are used mainly for cases where you want to access data that's in remote storages through HDFS. So the source of your data here is a remote store, say WASB or S3, and the destination is HDFS, right? And in these kind of mounts, the changes are bidirectional. So any changes that you do to the data in HDFS would be reflected back in your remote store, and similarly, any changes that happen to the data in the remote store are reflected back in HDFS. So the second kind of mounts are what we call as backup mounts. So in these mounts, the source of the data is actually HDFS. So you have, say, your on-prem cluster, and you want to back up your data to a remote store that is your cloud storage. Right? Your source is HDFS, and the destination is the remote store. And in this case, the changes are actually just unidirectional. So you only the changes that happen in HDFS are reflected back to the cloud store. So let's look at how these mounts should actually work in practice. So first, we'll talk about how reads would work in ephemeral mounts. So suppose you want to back up this particular you want to mount this particular subtree in your remote store into HDFS. So once the mount happens, you should be able to read the data in this subtree from HDFS. So whenever a client comes in and asks for a certain file, say DE, HDFS should be able to figure out that this file is actually not local, it's actually remote. It goes to the remote store, asks for the corresponding file, which is in this case CDE, gets the data back from the remote store, and sends it back to the client. So all of this magic happens with this new storage type called provided. So the provided storage type is used in our solution to donate for data that's actually remote from HDFS. So this is a peer to existing storage types in HDFS like RAM, SSD, and disk. And so now data nodes can have up to 4 different storage types, including the provided storage type. And the data in the remote storage is actually mapped to HDFS blocks that are in this provided storage type. So in HDFS today, you have this in the name node, you have 2 different parts: the namespace, which is stored in the FS name system, and it contains a mapping from files to a set of blocks that constitute this file. And the second part is the block manager, which looks at the block life cycle, figures out where the blocks are located in the cluster physically, and it maintains a mapping from the block IDs to the set of storage locations for this block. So we plug into the same abstraction. So for provided files, which is shown here by the violet names, so the provided file remote/bar, for example, is mapped again to a set of block IDs. And these block IDs are, however, mapped to a provided storage type. And this information is not sufficient for you to read what's in the remote store. So in addition to these, we also have what we call as a block alias. So the block alias is so we have a one-to-one mapping from a block ID to a block alias. And the block alias is something that is resolvable in the remote store. So it essentially contains of a simple 2-tuple. So one is a reference. For example, if you have file systems, say HDFS as your remote store, your reference can be a file URI, the offset of the from the start of the file and the length of this particular block, and a nonce. This is used for detecting changes in the versions of the file, and the nonce, for example, can be a simple inode ID in case of HDFS. On the other hand, if you have remote storage like S3, so your reference would be like a blob name, the offset and the length, and the nonce can be the e-tag ID of the blob. And we store this mapping from the block IDs to the block aliases in a key value store, and this can be this should be accessible by the name nodes and the data nodes, or it can be local to the name node, and either of them should work. And finally, we have these provided volumes on the data nodes, which actually help you read and write data from the remote store. So the provided volumes essentially implement a client that is capable of talking to the remote store. So in summary, you have these alias maps, which contain a mapping from your local HDFS block IDs to what's a tuple which can be resolvable in the remote store, and you have these provided storage types which indicate the data is actually remote. So let's look at an example of how this would work. So we want to mount the subtree, and we create what is an FS image, which is understandable by the name node today, and it contains a mirror of the metadata on the remote store. And the alias map, which essentially, as I just mentioned before, it contains a mapping from the block IDs to the block aliases. Also, the FS image contains these storage policies, which can help, so by default, it would be like each block has one replica and it's provided. So you could also change this when you create your FS image. So if you set the replication to be 2 and say it provided a disk, once the HDFS cluster starts up, we would start copying data into your HDFS cluster. So these can be consumed by the name node, and once a data node that's actually configured with the provided storage heartbeats in, the name node knows that the data is reachable. All the blocks that are in the alias map are reachable through the data nodes that have provided storage. So in provided storage, we do not do individual block reports for the different blocks in provided storage. This is in HDFS today. You actually report each blocks, but that doesn't hold for provided storage. We could have like millions and billions of blocks. So now, when a client actually comes in and asks for the location of a particular block, the block location is resolved in the block manager to one of the data nodes in the cluster that has a provided storage type configured, right? And so in this example, you get a location, say data node 2. Now the client can go to the data node 2 and ask for this provided block. The data node, looking at the block type, the storage type, can figure out that this is actually not local. It's in the remote store, and it contacts this alias map to figure out what is the location of this block on the remote storage. And it gets back this tuple, which is the location, the file URI, the offset and the length, and a GUID to detect conflicts. Using this information, the data node can read data from the remote store and send it back to the client. And as the data is going through the data node can cache it transparently. So you can do read-through caching, and for the next client that comes up and reads the same block, you now have the data local to your HDFS cluster. So this can significantly improve your performance whenever your remote stores have limited network connectivity like cloud stores. So going to writes in ephemeral mounts, so things like create directories and change permissions. So all these operations in ephemeral mounts are done synchronously on the remote namespace whenever a client initiates them. So when a remote namespace is actually a file system, the name node performs these operations on the remote namespace first and then does it locally. This ensures that if you have a failure in doing the operation on the remote namespace, you can send the failure notification back to the client and don't have to change any local state. So for blob stores, say like S3 or WASB, some of these operations may not actually make sense. So there are no real directories on blob stores, then you don't really have permissions there. So in these cases, we can actually not do these operations on the remote store and save on latency. So for the data operations, we actually plug into the existing write pipelines in HDFS. So when a client comes up, typically the pipeline has 3 data nodes to write 3 replicas. And when you initiate the pipeline, it's similar to what HDFS does today, but only for provided blocks, only one of the data nodes actually should have the provided storage type configured, and so that it can actually talk to the remote store. And we pass along the block alias in this pipeline so the data node knows where to actually write data in the remote store. So it uses this alias and talks to the remote store to actually write the data. So any failures in writing data to the remote store are handled similar to how the failures are handled in the write pipeline today, and we should be able to recover from them. So for backup mounts, this is a little different. So for ephemeral mounts, you have clients that come up and do these operations, but here we do the backup once, and a user would expect HDFS to keep continuously backing up this data. So we have a daemon running in the name node that once you create a backup mount, basically goes over all the information in the subtree that has to be backed up and goes and backs up each of these files. So we use an architecture similar to what the storage policy satisfier is being used. This is an ongoing work in Apache, and actually delegate the work of backing up individual files to the data node, to the different data nodes in the cluster. So this helps you not have relieve the pressure off the name node. So in this case, we essentially have a coordinated data node for each file that is being backed up, and it uses other data nodes in the cluster to actually back data up. And the data backup happens based on the capabilities of the remote store. So for example, for file systems that only support something like append, this is done block by block. So the coordinated data node goes to the first data node, backs up the block that it contains, and then you go to the second one and backs up the block, and then finally you do an ACK to the name node saying that this file is now backed up. So for blob stores, however, that's like S3 or WASB that support multi-part uploads, we can actually back up each of these blocks in parallel. So the coordinated data node initiates a multi-part upload, and then it talks to multiple name nodes at the same time, multiple data nodes in the same time to do the writes. And then eventually, when the writes are done, it does a finalize of the multi-part upload, and it can acknowledge to the name node saying that the file is being backed up. Now, while this backup is happening, you can have files in HDFS actually change. Right, so to solve this problem and to make sure that we have a consistent view of the files on the remote store, we use the snapshot feature in HDFS. So, whenever the mount is created, we do a snapshot of the subtree that's being backed up. We essentially back up the data and metadata of this snapshot. And when the backup actually finishes, we do a second snapshot and look at the differences between the second and the first snapshot. And if there is any difference, we would copy over the deltas over to the remote store, and we keep repeating this process until the mount is actually unmounted. So in all this work, we make a few assumptions. So we're not solving all the problems that in this case, but we try to work with limited semantics that the file system API provides. So we try to make something practical without having to have a strong coordination between the remote store and HDFS. So, and in most cases, it works for workloads, like for the typical big data workloads that people would run. So in particular, we assume that the churn is rare and it is relatively predictable. So in most of the cases, data is additive. So you consume data using an ETL process into a typical like a year, month, day, hour kind of a folder. And so we can use simple heuristics to resolve conflicts or to update the remote storage or the HDFS storage. And we also assume that clusters that actually mount remote stores are either producers or consumers. So if you were to go crazy and have multiple clusters that mount the same remote store in say Azure, we cannot, and each of them does reads and writes, then resolving conflicts between them is very hard if we just have the file system API between the remote store and the cloud. So we do not actually solve that problem. But in most cases where you have only consumers or producers, you should be able to use this to do something to improve your performance, especially when you're using this on the cloud scenario. And whenever you do have conflicts, these can be detected either on the reads. So whenever you do a read, we use an open by file ID kind of operation. So you know that. So that you know you're getting the version of the data that you expect to have. Or these are also detected on write. So if you're trying to write a file and the file already exists in the remote store, so we use a simple pluggable policy in this case, which can be configured with the administrator of the HDFS cluster. A very simple policy can be something like HDFS wins, right? So wherever we have conflicts, whatever is in HDFS is the source of the truth, and we overwrite what's in the backing store based on what's in HDFS. A different policy could be whenever you find files that are under conflict, you would rename all of the files that are under conflict to a known directory or following a standard convention, so that the administrator can later resolve these. So the current status, so all this work is being done on HDFS 9806 Jira in Apache, and we have a bunch of patches committed that enable you to do read-only mounts. So the prototype that's backup mounts is on GitHub. We'll post this link on Jira later today or tomorrow, and that was supposed to be the demo today. And going forward, we are going to look at how to actually create these mounts in running name nodes. So far the prototypes, what we have been doing is we have to start up name nodes to mount these FS images. So we would want to ideally mount these the remote stores in name nodes that are actually running in production today. So this is something that we want to look in the future. So if you're interested, come talk to us after the talk. And we have a lot of work that's going on. And this is joint work with, as Thomas mentioned, between Microsoft, us, and Western Digital guys. And thank you. If you have any questions, I can try to answer those. Yeah. Didn't. So the alias map, so the question is, in ephemeral mounts, the data in S3 is in S3, and who would actually come up with the alias map? So this is, so we have a tool that you could run so that when this basically scans over what's in S3, for example, and creates an FS image and the alias map. So it's and the FS image, you can try to give it where in HDFS you want the location, and that should be both the alias map and the FS image should be output of the tool. And you can start up name node that name node can actually read these outputs, and you can just have a regular HDFS name node after that.
So yeah, it's the name node has the block IDs, generates the block IDs. So the name node needs to control how this happens.
Is there a reason why alias map is separate and not part of FS image? Why is it not? Why do you embed it into FS image?
We could embed it into FS image. It's just that we do not change the FS image format. So it's just a site file. And so if we actually want a solution where the alias map is part of the name node's memory, right? So you are mounting, it's inside the name node memory, then it can be part of FS image, and we can read it when the FS image is loaded by the name node. But in the case where this is going to add more stuff into the name node, it's already a bottleneck. So if you want to keep it separate, right? So that's the case. There, the FS image, the alias match is separate. So you can run it in any key value store, and the name node and the data nodes can talk to that to get information from that. Yeah.
So in the case that the remote storage is an object store, right? Did you guys look into the renaming issue?
What do you mean the renaming issue?
For example, if you have a high job, then you're really tempting to a temporary folder, and then at the end on transaction commit, you will rename, and in HDFS that's a metadata change, but in an object store you're actually copying all of the data. I know that it's more general your work, but I was wondering if that particular case is some computation.
So part of what your question is what we're addressing with S3A, for instance, is addressed by the output committer, by changing how that works.
Right.
So here you have the mapping in HDFS. I'd have to think.
So one way you could do this is your temp is, the storage policy on your temp is not provided, right? So your temp is in HDFS. So all your output goes in HDFS. And then you do a rename to your destination that's actually provided. So the initial rename is a HDFS metadata operation. And if you set your write policy to the remote store as a write back policy, right? So so the rename happens in HDFS still, and then eventually the data gets persisted back to S3. Right? That's one way you could actually solve this problem.
Yeah. Right, true is a bad idea.
Yes.
With HDFS, there's always been sort of the limitation that you don't want to have a whole bunch of files. Bigger file is better than smaller files due to various reasons. Is that still the case with the remote file system in like S3 or something like that?
So yeah, again, if you want that deployment model, if you want billions of files, use the other model where you use the Hadoop compatible file systems where the namespace is in the object store. This one, of course, you're bringing the data into the name node. I think it plays nicely with HDFS Federation as well, where you can have multiple name nodes, manage multiple parts of the object store. But indeed, I know there's a lot of work ongoing on solving that name node problem. So if that name node problem gets solved by the community, we can benefit from that automatically.
Yes. Yeah.
Is there an ETA to merge into trunk?
Oh, ETA to merge into trunk. It's so for the read-only part is almost ready. So we have a couple of Jira pending, which is blocked on another Jira. So if that is done, we should be able to merge into trunk the read-only part. The write right now is still a prototype. We need to polish a few things there, and but the read-only part we should try. We can try to at least call for a merge in a month or so. Yeah. Questions? Good.
It's time. Thanks.
Thanks.